So this is how I had to write my own benchmarking library at some point, because existing libraries just didn't scale. And like my background is I used to work on a bunch on performance. Like my previous talks were about generalizing radix sort, which everyone should be using instead of comparison-based sorting, and hash tables. And I blog about things like how the min-max heap is better than a binary heap because you get both the min and the max, and it's also faster at the same time, which is nice. But each of these, I wrote like a huge number of benchmarks, and eventually you just want your own benchmarking library. So, mostly I want to get a handle on the combinatorial explosion of benchmarks, because you just want to test all kinds of things. And the full suite would take like months to run. I don't even know how long it would take. I want to have a UI, because whenever you take something serious, you always end up writing a UI in the end, I think. And code best practices, like there was a library called Stabilizer, whose point was, one big problem with benchmarks is even if you just recompile your code, you often get wildly different results just because alignment changes. And so what Stabilizer would do is it would like randomize memory layouts and would randomize heap allocations. This library doesn't exist anymore, it's not maintained, but like the least I can do is like each time I run the benchmark, run with new ASR, like run with new randomized memory layout, even if I can't do the even if I can't get like the heap allocations randomized. Let me see if I can pull this over here. We're just gonna run. I'm just gonna demo it. That's actually the whole lightning talk. I'm just gonna. This is my UI. There's nothing in it, but I can add an executable. This is very much written by me for myself. So it has graphs and tags, and it just starts running the benchmarks. And this is just like a benchmark that measures like memory stuff. It is very spiky right now because I was running these earlier, and like it's rerunning them right now. Every time it reruns the benchmark, it like does it in a new process with like new randomization. I can draw as points. We can see like these over here were run many times and these were not, and it's crazy noisy, but that's also because I'm on battery, but that's okay. I like having the lines. I like having interactive interaction, so I can like see what's going on. I get lots of precision from this because I always have like a baseline benchmark. For every benchmark has to provide its baseline that gets subtracted out. So like here's like sequential memory access, which apparently takes 1/10 of a nanosecond, which I trust this number roughly. And because if you go up to bigger arrays, it says it now takes 1/4 of a nanosecond to do a sequential memory access. Like just iterate along an array, every access takes this amount of time. I trust these. Well, this is now where you get the spike, the noisiness, because it's running a new benchmark while I'm on battery. So the baseline was slower than the actual benchmark. So that's why you get negative numbers. But it'll run over and over again. Eventually, it'll stabilize. So like, let me put a more real example, which was the heap work. So the thing you see here, actually, let me just make this big, is I have an insane number of tags of different things I might want to check. I have all my, let me just turn off these things. I have different kinds of heaps. Let me turn them all off except for standard heap, just so we don't have crazy number of lines. Well, this one's interesting, dairy heap I left on because just to see like every time I try a new thing, I just add a new tag and I get my full like explosion of all the benchmarks. I can run them again, but let me just turn that off to be more reasonable. So here's like standard heap. Let me just compare make compared to push. So when I plot, I also decided like on one standard way of visualizing these benchmarks, which is I always just do a line graph and I divide by the number of elements. So when I plot make here, this is like make heap, I divide by the number of elements. So this is like the time for like, this is 1024 and it took 1024 times as long basically. So one element took like 7 nanoseconds. And like, if you push over and over again, it takes longer basically. And like, you might think it's log n, but like log n actually on this graph should look like this, where it just keeps going up because it's the log axis on the y. And push is actually like constant time for a big enough heap, which makes sense because I'm inserting random things and random things don't trickle up very much in a heap. When you just keep on pushing random things into a heap, they just always stay like at the lowest level. Then the other interesting things is since it's this new executable anyways, I can like easily compare like Clang versus GTC, and I just get like the same lines. I can compare like Clang versus the different flags. So here I have, let me turn off GCC. Let me turn off, nope, I wanted this one. I'm just going to make this smaller to have the noisy stuff out of the way. Here is popping from a heap with 2 different compiler flags for Clang. One of them is 3 times slower than the other one. This is the CMOV converter, where Clang for some reason does not like conditional moves and replaces them with actual if-else branches, which is a terrible thing to do for heaps. But like mainly the point is like I got a handle on combinatorial explosion. I can see all kinds of things. I'm happy I can explore all my benchmarks. It's good. I have many other features that I wanted to show, but no time. Oh, and also, yeah, I will. Yes.